All right, so let me just quickly review what we have said. Very quickly, I started first by introducing the engineering dynamics, MEE 420. It's all about the study of how moving objects behave. Dynamics is the part of mechanics that studies movements and its causes. So when we study the motion of objects and why it changes in motion, we're talking about dynamics. I said earlier that every object remains the way they are or the position they are, except a force acts on it. And when we just study motion as it is, we're talking about kinematics. But when we look at the causes of the motion and what changes the object to move, we're talking about dynamics. We've gone to we delved into the Newton's law, which is the basic of every physics and science engineering student, and we came to understand that the first law tells us that a body will remain at rest or in a constant or moving at a constant velocity unless it is acted upon by an unbalanced or external force. Number two, the second law says that the force experienced by an object, excuse me, is proportional to its mass multiplied by the acceleration it experiences. So an object with a greater mass and a faster acceleration produces a greater force. That means that if you hit a nail with a heavy hammer, but you are slow in hitting it very slowly, it's not necessary that it will give as much force as using the same hammer on a faster. The third law states that if two bodies exert a force on one another, the forces are equal in magnitude, but in opposite direction. In opposite direction. Next slide. All right, let us look at vectors. Vectors, and we're already familiar with what vectors are from our junior classes. Vectors are quantities that has both magnitude and direction. They have magnitude, they have quantities, and they are in specific direction. It is typically represented by an arrow whose direction is the same as that of the quantity and whose length is proportional to the quantity's magnitude. Let me take that again. It is typically represented by an arrow whose direction is the same as that of the quantity and whose length is proportional to the quantity's magnitude. So if it is 3 cm or 3 meters, then it is the same proportionality as the quantity's magnitude. So although a vector has magnitude and direction, it does not have a position. It does not have a position. No. It does not have a position. So you can see the diagram there. On my slide, it simply shows the different the direction A. It shows the direction of A and B, which is also the same thing as B and A. They do not, it does not have a position, but it has magnitude and direction. Examples of vectors in nature are velocity, momentum, force, electromagnetic fields, and weight. Because weight is a force that is produced by the acceleration of gravity acting on a mass. Let us look at what is called reference frames. Now, strictly speaking, Newton's laws of motion are valid only in a coordinate system at rest with respect to the fixed stars. Newton's law of motion only work, are only genuine, are only possible when the coordinates, only in a coordinate system that is at rest with respect to the fixed stars. Okay, such a system is known, of course, as the Newtonian or inertial reference frame. The laws are also valid in any set of rigid axes moving with constant velocity and without rotation relative to the initial frame. This concept is known as the principle of Newtonian or Galilean relativity. So basically, for Newton's law of motion to work, it must be considered under some fixed condition. It must be considered with coordinate systems that are at rest. So a coordinate system attached to the Earth is not an inertial reference. It's not an inertial reference frame because the Earth rotates and is accelerated with respect to the sun. Therefore, and this is where we are going, therefore, to describe the position of a point that moves relative to a body that is moving relative to the Earth, it is usually convenient to use what is called a reference frame attached to the moving body. So for us to be able to describe the position of a point or an object that moves relative to a body that is moving relative to the Earth, it is usually convenient to use what is called a reference frame. So what is a reference frame? So what is a reference frame? Now, a reference frame, a reference frame that is otherwise called a frame of reference in dynamics is a system of graduated lines symbolically attached to a body that serve to describe the position of points relative to the body. Now, those points, those graduated lines are just symbols. They symbolically show or describe the position of points relative to that body. It's also an abstract coordinate system whose origin, orientation, and scale are specified by a set of reference points or geometric points whose position whose position whose position is identified both mathematically and physically. I want you to look at this diagram that is just below that my cursor is hovering on. You see an object. This object is the coordinates are mapped out in 3 dimensions. You see the x-axis, the y-axis, and the z-axis, indicative of the length, breadth, and height, or in 3 dimensions. So at this particular point O here, we can map some graduated lines symbolically to indicate the position of the points relative to this body that I am indicating here. So that is a frame of reference. Let us look at the next slide. Reference frame changes and relative motion. Now, everything up to this point assumes that we are using a fixed, previously agreed upon reference frame. Basically, this is just an origin and a set of axes along which to measure our coordinates as shown in the last slide figure. There are, however, a number of situations in physics that call for the use of different reference frames, and more importantly, that require us to convert various physical quantities from one reference frame to another. For instance, just listen to this example. Imagine you're on a boat on a river and you want to row downstream. You are moving with a certain velocity relative to the water around you. Remember that as you are rowing, the water is also moving. The water is not stagnant. The water is not stagnant. Let me explain something. But the water itself is flowing with a different velocity relative to the shore. And your actual velocity relative to the shore is the sum of these two quantities. Let me show you something here. Let me show you something. Let me use a whiteboard. All right, look at this. The river is flowing this way. The river is flowing from
from this position to this position, left to right. But now you want to move from this point A to B. You want to move from here to here. Now, if you have ever gone on a boat ride before, you know that you cannot just row your boat from A to B. You cannot row your boat from A to B. You cannot row your boat from A to B, because the river is moving from this position. Let me call this position X, and it's moving from X to Y. I hope all of you can hear me and you can see my illustration on the slide. If you can hear me and you can see my illustration on the slide, can you just type 1-1? Let me be sure you are following. If you can hear me and you can see this illustration I'm typing now, type 1-1. Okay, good. So let me explain again. A river is flowing this way from X to Y, and you are in A and you want to go from A to B. Now, you cannot just go from A to B, because by the time you are going from A to B, the river would have moved you to a position that is maybe C. Would have moved you to this position C, because it's moving. So what do you need to do? What you need to do is that you don't need to move from A to B. What you need to do is move from A to B1, this place, this one. So that by the time the river is flowing this way, it will be acting positive for you and taking you to this position. But if you go this way, you'll be swimming, or you'll be rowing against the tide, because the tide is going this way and you are also going that way. It will move you away, but you want to get to B. So what would you do? You go this way so that it will move you to this position and you come here. So that is what we should do. So in these are reference frame. This reference frame is different from this reference frame. So there are two reference frames here that we have to look at. All right, so let's continue. Probably you need to increase your, George, you need to increase your volume. I'm practically shouting here. I think everybody else can hear me. So let me continue with our slide. All right. So that is what reference frames are all about, and changes with relative motion. So ships generally have to do this kind of calculation all the time. So it involves calculation. It involves specific calculation. The ships need to do that calculation. Aeroplanes need to do that calculation. And in aeroplanes, it's called airspeed, which is the speed of a plane relative to the air around it. But that air is usually moving at a substantial speed relative to the Earth. Just 1 second. All right, next slide. All right, let us look at the following in while we're still talking about